Okay, so for the exercise 1, let's read the question. We talk about a certain fluid at 10 bar is contained in a cylinder behind a piston. So let's draw it to get it in clear picture. Okay, so this is your piston cylinder assembly. Okay, so suppose this is your cylinder. Okay, and this is what we call piston. Similar arrangement you can find in your car. If you have 4-cylinder, that we call 4-cylinder engine, right? Or maybe 6-cylinder or so on. So this is something, the same concept. So there's a fluid inside that one. Let's say the fluid is unknown in this case. It should be whatever type it should be. And the pressure of the fluid is 10 bar. Okay. 10 bar contained in a cylinder behind a piston. The initial volume being is 0.05 cubic meter. So this is our V1, which is 0.05 cubic meter at this point. Okay. Calculate the work done by the fluid when it expands reversely at constant pressure to a final volume of 0.2 cubic meter. So let's say the second position is here. The piston comes to this point, which is now become V2, okay, which is equals to 0.2 cubic meter in this case, right? So the question is calculate the work done, right? Let's calculate the work done. Okay, so we have to find out the work done. So the formula for finding the work done is W equals to, here we have the pressure and volume terms. Pressure is constant, it's mentioned in the question, right? For a constant pressure, here it is, right? So for that case, we can say work done equals to P dot dV, right? From point 1 to T, right? So as the piston move from point 1, let's say this is point 1, this point 2, what is the work done required, right? Not to forget, here we have to write down the negative sign because calculate the work done by the system, by the gas or the fluid, right? So the fluid expends some energy to perform the job, right? It's a natural law. So if pressure is constant, we can further simplify this formula. We can write P dot into bracket V2 minus V1, right? Because P is constant, minus sign is still there. Now pressure is 10 bar they have given. Now we just have to put out the value. Pressure is 10 bar given in the question. So we can write 10. Remember 1 bar equals to 100 kilopascal from the previous video, right? So 10 bar means 10 into 100 kilopascal times V2 minus V1, which is 0.2 minus 0.05, right? If you do all the math, the work done equals to 150 kilojoule, which is minus, having the minus sign, right? That means while performing the job, the system loses some energy, and that is why it is in the minus sign. Okay, so that's about the first answer. Let's move on to the exercise 2. Okay, let's talk about air compressor, right? In an air compressor, the compression takes place at constant internal energy, right? Yes, right, constant internal energy. Constant internal energy, which is U is representing internal energy here, okay? So constant mean whatever is coming inside the compressor, the internal energy is the same as it's going out of the system. So U1 and U2 we can say this is the same. U1 and U2 is the same because in this question they have assumed, right? Mostly, if you understand what is the air compressor, which is a device which compresses the gas, reduces its volume, and increases the pressure, right? That is the purpose of the air compressor, right? So we don't have any kind of the heat addition to that, but we have a negligible amount of heat that being generated because of compressing the gas to smaller areas, and in that case the pressure goes higher and the gas molecules comes together. A little bit of the temperature change will be there, but the question directly mentioned the compression takes place at constant internal energy, so we have to stick to that point. Okay, so U1 and U2 is the same, right? We can also say that U2 minus U1 equals to 0, right? Let's say 5 from one side, 5 is coming and 5 is going, just for example. 5 minus 5 is 0. Or we can further say delta U equals to 0 in this question, right? Let's say I'm just drawing a general block diagram. Suppose the air is coming from this side, and this is a U1, and air is going to this side, that is the U2, and these two are the same, right? So during the compression stroke, and we know that when you have the piston and cylinder assembly, because of the friction between these two, there is a heat regeneration. That heat we must need to remove, right? So that removed heat from the compressor to the outside atmosphere, which is 50 kilojoule of heat are rejected to the outside, right? So if heat is rejected from any system, it means they are losing some form of energy. So it is minus sign 50 kilojoule. So the question is calculate the work input for the compressor. Now in this question, just focus on the input, right? How much work we required to run the compression, right? To run the compressor. Similar that if you have a compressor, how you are going to run that one, right? You must need some form of piston cylinder assemblies, right? You may need some kind of other mechanical device which rotate those, and then we get those compression. So in this case, Q is minus 50 kilojoule, delta U equals to 0. And the question is calculate the work input. Pretty straightforward. Apply the first law of thermodynamics, which is change in internal energy is equals to Q plus W, right? Delta U in the question, it is 0, so that's 0. Q is minus 50 kilojoule plus W, right? So work equals to, just rearrange this one, which is 50 kilojoule per kilogram. So for 1 kilogram of air compression, we need 50 kilojoule of work. And these units are in kilojoule per kilogram because they're talking about that. Right? So this here we have the positive 50 kilojoule. The work is positive here because the question says the work is input, right? So in this case, the system gets some energy. So the sign is positive. Okay, the last one for this session, which is exercise 3rd. Again, they are talking about the compression stroke, right? This is again the piston cylinder assembly. Okay, so suppose this is your cylinder and these are the piston. Okay, and inside the piston, the compression stroke of a gas engine. The work done on the gas by the piston is 70 kilojoule per kilogram. So suppose this piston doing some work to this fluid, right? Some work to this fluid, okay, which is equals to 70 kilojoule per kilogram. And we have piston cylinder assembly. We must need some coolant or cooling water to keep the cylinder temperature maintained, right? Which is why we have some heat rejection. So the heat rejection is 42 kilojoule per kilogram of air. So it is rejecting from the system, which must be in minus, right? Then apply the first law of thermodynamics, which is delta U, which is change in internal energy equals to Q plus W. Q is minus 40 plus W is 70, and change in internal energy here is 28 kilojoule, right? So 28 kilojoule per kilogram, right? So if you see this one, delta U, okay, 28 kilojoule kilogram. In exercise 2, the question says that the internal energy is constant, so we assume 0. But in this question, they have not said anything, but they just ask what is that delta U. Okay, that's for exercise 3. But one more thing I want to add, not related to the question, for the internal energy U is the function of the temperature. So as the temperature goes higher, right, the internal energy goes higher. So this is a function of temperature. That's for now. The remaining 4 questions from these tutorials are based on steady flow energy equation. So there will be another video for that, because that is changing a little bit from this side. We have lots of equations that we have to discuss prior to coming. Take care.